So I welcome you all with warm welcome, sir. Please, we can continue and your lecture. Thank you, sir, for having us.
Okay, so good afternoon, everybody, and thanks the presenter who introduced nicely. So without any delay, so let's start the topic, future perspectives of memristive devices. This is my mail ID, it's given below. So if any queries which cannot be completed within the limited time, anybody can ask me through email and these things. So before going to next, I would like to ask all the participants, am I audible clearly or my screen is visible clearly to all of you?
Yes, sir. You are clearly audible and your slide is enlarged.
Is it okay now?
Yes, sir, it is okay.
Okay. Okay. So let's start the topic. So this is the flow of my talk today. So I will first describe the importance of memristive. This is a comparatively a new field. So we should know the importance and how it can be utilized for our recent and latest technologies. Then we'll be elaborating some brief theoretical aspects, and this followed by some brief review of very recent research, particularly in the device aspect. I'll cover the device aspect of this memristive and also the challenges, and finally the scope of further research and which area we can do, we can contribute, our students or participants can contribute. That will be discussed in detail. So first of all, concerning the importance of this resistive memory, let us consider the present day computer architecture, and this is well known as a von Neumann architecture. Here you can see, so there are several units, namely the control unit, processing unit, and memory unit connected with input and output devices. So in this architecture, mainly there is a continuous to and fro data flow from the processing unit to the to the memory unit, and this unit, this process takes lots of time, and we are witnessed with the thing that we have been increasing the processor speed, that means clock speed, to reach in the gigahertz range, but still the interconnects between processor unit and memory remains in the order of some 1000 or more megahertz. So basically the overall speed of the computational device is limited by this speed limitation of to and fro communication from the processing unit to the memory unit. And this can be overcome by the technique of this resistive memory, the new technology. So how? Let us see. We just focus on some recent technologies. So you know the present day demand is AI/ML. So everything we are doing in AI/ML, but AI/ML processing, it needs huge computation. So for example, in a small part, if we see a particular or a single perceptron in a AI/ML environment or in neural network, so this particular node receives signal from many nodes, and after getting it multiplied with the weight, it is added in the perceptron. And similarly, there are several such kind of perceptrons in a particular layer, and also the neural network architecture consists of such layers as more than 3, 4, etc. So from these, we can, or you can imagine the level of hugeness in the computation process. So if we do these computation, till now we are doing, if we do these types of computation using the conventional computer technology, that is von Neumann architecture, it needs huge time, and that speed due to the limitation of the to and fro communication that I already discussed. But if we see further, this already I told that the neural network consists of several layers, and each layers there are huge number of nodes, and each node needs huge number of computation. So the problems of this computation is the speed. But in another aspect, if we see the memory, whatever we are using at as on date, that is mainly the CMOS memories. And here we store the data or information in form of charge, basically, it's 0 or 1. But you know, charge is not possible to measure directly. That's why we, by using electronic circuitry, we generally convert this charge either into voltage or into current. And in this form of voltage or current, we store the information or data in the memory. And for that, we need to take help of CMOS memories. And mostly, the capacitor unit plays very important role in the storage process. Say, capacitor, when it is charged, a voltage is developed across its two terminals. Similarly, when it discharges, say, voltage reduces. So in this way, we convert the charge to voltage through a capacitor, and similarly, we can store and we can read out the information from this memory. So involvement of capacitor is very crucial. And again, the problem of this reading and extracting data from this type of memory needs the charging and discharging of capacitor, which is again very time consuming process and mainly limited by the RC time constant. This is the basic, this is the fundamentals of this thing. Now, if you see the advancement of CMOS memories through, say, CMOS inverter, so there also the charging discharging mechanism is associated. And for low power operation of these memories, because another aspect parallelly we are taking, that is the low power operation. So in that case, you see in a CMOS scaling, that is a VDD scaling is required. So our intention is to reduce the VDD voltage to reduce the power consumption of a memory that is storing and reading out from that memory. But if you reduce the VDD voltage, that is the voltage at the VDD voltage is well known for the CMOS memories. So at the same time, threshold voltage needs to be reduced also. Why? Because you know the on current basically depends on the range between VTH to VDD. So if you reduce VDD without reducing VTH, so your on current collapses, and that ultimately will increase the delay. So parallelly, what we conclude that VTH also need to be reduced. But what happens if we reduce VTH? If we reduce VTH, the off current will increase exponentially due to its nature. Hello? Hello? Due to its nature. So that's why VTH scaling is required. So parallelly, VTH should be reduced. But you know, all these scaling hues of research works have already been carried out, and ultimately it is saturated up to say 0.5, 0.6 volt in this range. VTH scaling is saturated. Now, another aspect in a DRAM, CMOS-based DRAM technique, there is a output coupling capacitance, that is a load capacitance CL. There also, if you try to store the charge or information in form of capacitor charging, so there also you need to have you have to maintain a critical level of charge, and for that critical level of charge you cannot reduce the size or this power too much, so that we are limited by the speed of reading in a memory or writing in a memory. So in addition to the to and fro communication from processing unit to memory, memory itself has some limitation, some delay due to reading and writing. So these both together impose a real challenge in implementing the AI/ML architecture in a conventional computational device. So what is the solution? Solution is actually the in-memory computation. So if we can embed the memory within the computational device, this is the main target, so that we can reduce the to and fro communication. And for that, we should have a crossbar architecture. We will be going one by one. And in a crossbar, you can assume that there are some rows and columns, and every crossing of row and column, there is a memory which can store the data, as well as the data which is stored here that can be varied. So parallelly, we can change the data and we can store the data. So a matrix-like structure of memories in a crossbar architecture will be capable of using the matrix operations like matrix multiplication. So the storage of information by physical quantity other than charge is required, because I told you the charge can be stored in the form of volt or current, and that needs some time. So these both can be achieved by using a resistive memory. If we think of a memory which based on the resistance property, and the resistance of that memory can be changed by some control signal. So this is the basis of the resistive memory. So there are different types of alternative memories, say resistive RAM, phase change RAM, magnetic RAM, ferromagnetic RAM here. But here in this lecture, we will be mainly focusing the resistive RAM or phase change RAM. So what is the fundamentals of this resistive memory? Instead of storing the information in terms of charge, here we store the information in terms of resistivity or conductivity. This is the first thing. And that's why its name is memristor. And this memristor aided logic are called magic. So this was first proposed by Leon Chua, all of you perhaps know, in 1971. Basically, it is a structure consists of metal insulator metal. So that is called MEM structure. So basically, one insulator layer is sandwiched between two metal layers. Now, instead of a conventional resistor where we get the linear characteristics between voltage and current, that means if we take a resistance of 1 kilo ohm, say, if we change the voltage across this, current through this resistor will also change linearly, and we are getting a zero crossing linear curve in that case. But if we have a memory, or if we have a resistance in such a way that if we change the voltage across its two terminals, its resistivity itself changes. In case of conventional resistance, the curve VI curve, that is slope of VI curve, which indicates the inverse of resistance, that will remain same. That is a constant. So that is constant resistance. But to get a variable resistance, we should have a variable slope curve. So for example, in this figure, if you see from the 0 volt, if we start increasing the voltage, gradually current increases through a red line as shown here. Up to a particular voltage, very small current is being flowed through this resistance, but suddenly it jumps to a high value of current. That means here the change of slope is very drastic. We can say the resistance drastically reduces in this point. So that means throughout this journey from 0 volt to this volt, we obtained a low current and also very high current. And when it is flowing very high current, then it is called set state. So resistance is becoming very low. Now, if we do the reverse operation, suppose we are now reducing the voltage from a particular value to again 0. So initially, current will not change. So this path. So current will not change means resistance remains low. But from this value, this voltage, it then reduces to 0 again. That is here in this case, you see the resistance is almost constant. So that is ohms, just like a ohmic behavior here. And similarly, if we interchange the polarity of the voltage across the resistor, that is in negative side. So current initially you see very low in a red line it is flowing, and suddenly it reduces, it increases to a very high value, and again when we trace back to 0, it will reduces to 0 current, but through a different path. That means we can observe here it is unlike a ohmic behavior, a particular resistance which behaves like a variable resistance. For a particular range of voltage, it gives a low resistance. For other region of voltage, it gives a high resistance. So this is called the variable resistance, and this is also the building block of a memristor. And the symbol of this memristor, people have decided to represent in this way. So with these basic fundamentals, let us again insert into more thing. Suppose till now we have relationships like C is equal to Q is equal to C into V. That means in any capacitor, we know that is change in charge dQ will be some constant into change in voltage. I mentioned that charge is generally stored in terms of either voltage or current. So change in charge, basically dQ, is stored in the form of change in voltage in a capacitor. Similarly, in a resistor, this R is means dV, that is change in voltage, is well some constant into change in current. And also, if we have some inductor type behavior, we can have change in current is proportional to the change in EMF generation. But there is a missing between the relationship between change in charge with the change in flux, because ultimately they are dependent. If you observe, the change in current is related to change in charge is related to the change in voltage, or change in charge is related to the change in current, and this current again changing in the flux. So ultimately the change in charge can be related with the flux. So this is the new equation people are thinking for the memristor. So this the fourth law, this they are proposing, and this in this same way, this is told that for memristor, if we say the symbol is M and memristance is the property, and then we can say this M memristance is equal to d phi m dq. So change in flux change with respect to the charge change. So in terms of this flux change also we can store the information. This is the basic things of this. Now if we enter into the device picture. How is it possible? How is it possible to change the resistance of a device with voltage? So I told earlier that this is a metal insulator metal structure, and you see generally transition metal oxide with some oxygen vacancy as insulator is used. Mostly the transition metal oxide, so say some TiO2, some zinc oxide, sometimes some gallium oxide. These materials are used as an insulator. So what is the special characteristics? Transition metal means its state changes, and also here the technology is you have to make oxide in such a way that there is a vacancy. There are some vacancies of oxygen. That means suppose we have SnO2, tin oxide is a complete formula. But if we can make SnO, that is we are intentionally putting less oxygen, so there is a lack of oxygen. So there some oxygen vacancy will be created. And that oxygen vacancy is treated as a ions, because oxygen vacancy means lack of oxygen. So this may be treated as a positive ions. So normally when there is no treatment or nothing control is there, so this behaves like an insulator. So you don't get any current through this. That means if you have a structure in the first figure, so in the top there is a electrode, contact material is metal, and bottom also a different metal or maybe same metal. I have used different colors for different metal. In between there is oxide, but in this oxide oxygen vacancies are scattered in a distributed way. Now if we apply some voltage, suppose in top electrode positive and negative and bottom electrode negative, so these oxygen vacancies will try to align a particular path. This is called filament. Formation of this nanoionic filament, this can give us a path of flow of current from top metal electrode to bottom metal electrode. That means there is a path is established. So we can say the resistance becomes drastically low here. So initially it was high. So that the characteristics we have described. Similarly, if we keep on increasing the voltage, there will be more and more formation of ions. This is called nanoionic formation. This is one explanation of memristor device. Now, how so resistance is changed, but how it acts as a memory? Memory means suppose you have made this filament by applying this voltage. Now you suddenly make off the voltage, there is switch off the voltage source. Still, this filament remains here. That means the resistivity, the conductivity, rather to tell conductivity, whatever you achieve, that will remain even after switch off. So this is called non-volatile in nature. So the value of the resistance, which is already decided, that will remain stored. So that is the technique called storing information in terms of resistance. And also the change in resistance you can control by changing the voltage also. That means with the help of some control signal, you can change the data in the form of resistance, not in the form of charge. So this is the main advantage. So this is the basic principle of the memristive device, the nanoionic film formation, or this is called film theory. But this is not the end. So this is the starting. So many other things are coming. When suppose it has two states, one is low resistance state called LRS, another is called high resistance state when it is no voltage is there. So HRS, these two states are there. But the problem is, can we guarantee these resistance value will change in a similar fashion if we repeatedly put the same voltage? That means suppose we are applying a voltage, say 0, and we are increasing up to 4 volt. So its resistance suddenly reduces at 4 volt. Now we again retrace the voltage from 4 volt to 0 volt. So its resistance again becomes high. Now, second time, if we again increase the voltage from 0 to 4 volt, can we have same formation of filament? No, that we cannot give guarantee. So this is the main challenge. So we are playing with the morphological change, so that cannot be controlled so easily. So cycle to cycle, there will be a different resistance value. So that means this is the main problem. If we like to have this type of unit as a perceptron of a AIML unit, so we need to assure that if we apply the voltage again and again, the same voltage for same voltage, we have to obtain same resistance value. Otherwise, it will total data will be collapsed things. So this is the main thing. After this, some other peoples also tried to explain the behavior in terms of band diagram and other things, and lots of research work have been carried out based on changing different oxide materials. Then main purpose was to control the deterministic behavior, that is desired behavior every time. So for that, if we change the material and if we see the band diagram scenario, a quick look for a cesium oxide, say tungsten oxide, some indium tin oxide with some metal electrodes, say silver, gold, etc. And if you see the structure, because MIM, metal insulator metal, so there is an interface between metal and insulator. And you see there is a difference in work function, so I mean in affinity values, in band gap, other things. So for example, in this picture you see there are different values of electron affinity and work function for cesium oxide, tungsten oxide. And if we now make an interface between silver with any of these oxides, it looks, that depends on the band diagram. So this is the band diagram formation formed after making this MIM structure and also the interface structure. Even people tried to make use of two different kinds of oxide layers as an insulator. See, instead of single insulator, if we can have two types of insulators in between two metal electrodes, that may also serve more deterministic performance. So that's why the reducing the variability was the main target. Anyway, so here also I have pictorially presented some nanoionic film formation in application of voltage, but again it is totally stoichiometric change and you don't have full control on this behavior. Now this is very easy to develop because this is very straightforward. So that's why I would like to have a quick look about the fabrication of this MIM structure, metal insulator metal structure. So it can be done in two phases. In first phase, you see, suppose you are starting with a wafer, choice of wafer is also important. So this is an example by a research group. So they use basically a cyclic olefin copolymer substrate called COC polymer, COC substrate. This is very important. And on this substrate, initially, suppose the gold, thin layer of gold is deposited by a sputtering unit. So sputtering is a system, the physical vapor deposition technique. On this AU deposited layer, you can make a pattern. Pattern means in which region you want to remain the, you want to maintain the contacts, and other region you can lift off or you can remove. For that, lithography technique is used. So and these are the well-known techniques by putting the layer of photoresist and it can be deposited by a spin coater followed by some baking, means heating of these or at a different temperature is done. And after this, wafer is subjected to a ultraviolet light via some mask. That is, if you put some mask on this particular region and if you incident ultraviolet ray, so the rest of the region where the ultraviolet ray falls, they becomes very hard and rest of the portion remains soft. After this, if you etch by a proper solution, you can remove the you can remain the soft portion and you can remove the soft portion and you can remain the hard portion. So there are different techniques. The positive photoresist, negative photoresist are available. So based on that, you have to choose. So ultimately, after etching of these unmasked region, you can have these are the gold regions. And now in the phase 2, you can do very easily. So oxygen plasma, first you have to insert by putting some mask on these, because otherwise oxygen plasma will hit the gold portions also. So oxygen plasma is generally put due to increase the weightability or adhesion force of say oxide flakes, because if we put say graphene oxide or other oxide or whatever, so this oxygen plasma should be treated. And then if you put a drop of again the proper solution for a particular oxide, and if you spin coat it, so this coating of graphene oxide will be on this except this portion. And then if you can make some annealing, so the except this gold portion, some oxide, graphene oxide will be deposited in between this. And so finally you can see the picture. So this is metal, then there is a oxide insulator, and then is metal. So a series of memristor you can deposit on a single step, single process. So batch processing. So be careful about the dimensions. These are the gaps, generally in micron or millimeter, this thing, and it is also being reduced to nanometer to have a better control. Anyway, so this is very easy, and that's why lots of people have done research work on this, and they have done the characteristics. And again, the similar characteristics people have obtained. You see, during the 0 to plus some voltage scanning, you are getting the characteristics is following a different path, and when it is retracing from some positive voltage to 0 volt, it is following a different path. So there is a hysteresis which indicates there is a storage can be possible. But the problem is the cycle to cycle variability. It can be observed from an experimental result I have taken from a group. You see the run different for different runs, you can have a different types of characteristics. So what I mentioned, that is variability. This is really a thing, challenging thing. Also, another important thing is temperature sensitivity, because if you change slight temperature, the morphological change of the insulator material also very severe. And that means if you make a computational device with the help of this structure MIM, and if you operate this device at a different ambient temperature, you are getting different results. So this is not acceptable at all. That's why temperature sensitivity is also a challenge. So first of all, we can achieve that variability, cycle to cycle variability, and temperature sensitivity, and the morphological change. These are the real challenge of this developing or getting the good result in memristor. So here's an example of a technique for understanding I want to mention here. So how an array of this memristor unit can be utilized to compute or to put some digital operation and analog operation. So for example, here if you see, so these are the structure. Please concentrate on this. The left side, you see, so there are 3 resistors, the variable resistance, the memristor I have put, and the connections are you saw, that is a dot lines are shown here. So these are the connections, and these 2 input lines, and this is the output lines. So connection of memristors are between these 2 dots. So now in an input line 1, input 1 is connected to a voltage. So if you control this voltage, obviously the M1 value will change. So maybe 0 or maybe 1. Similarly, by controlling input 2, you can control the M2 value. So suppose these both are a very low resistance state, M1 and M2, and for a particular voltage combination. So whatever the vertical line, the current is flowing, so that will be flowing through this M1 resistance and M2 resistance, and ultimately very less amount of current will be passing here. So ultimately you are getting nothing, so output will be very low. Similarly, another thing, if you have a very high resistance, so no current will be almost passing. So basically here you will get a high value. So that means in this way you can have a NOR gate. Similarly, other structure also you can obtain for the NAND gate, OR gate, AND gate, NOR gate by controlling the resistance of the thing. So these are the circuit can be obtained by arraying some memristors. So similarly, for analog operations, so for matrix multiplication, suppose you have the horizontal lines, they are connected with one end of memristors. Another line is connected to the end of another set of memristors in this way. And the vertical line considers the flow of current. So voltage when is flowing through this, and you are getting the current, the sum of all these voltages through these resistances, and they are controlled by some voltage V1, V2, V3, and this is the resistance value. So ultimately, the I1, I2, I3, this set you are getting, say I1 will be sum of V1 into G1 1 plus V2 into G12 plus V3 into G13 in this way. So I1 we are getting. Similarly, I2 will be so V1 into G21 plus V2 into G22 plus V3 into G23. In this way, a matrix type of vector matrix multiplication by choosing particular resistances you can perform. This is another more clear crossbar architecture. You see, these are the voltage lines and current lines. They are there. So this input voltage, this is the deep purple color is showing, and these horizontal lines, they are taking the output current, and in between they are connected by some memristor unit. So this can be fabricated on a single go in a fabrication techniques. So these are the main advantages. So in this way, an array of the architecture, the crossbar architecture or crossbar mechanism or array of memristors you can have. But again, the challenge is variability of each resistor value, memristor value, due to morphological change and its sensitivity. Now, how to overcome? This is the main question. This was from the after invention of these things. So many people have been working, and first of all, to reduce the variability, many researchers have tried to reduce the thickness of oxide. So as per their proposal, if we reduce the thickness of oxide, we should have a more control on the nanoionic film, because less number of nanoionic film, less number of oxygen vacancy will be there, and we can control the less number of oxygen vacancy states. So the number of vacancy control is the main technique behind this. That is called vacancy engineering in a transitional metal oxides. Very recently, so in last decade, so use of 2D materials. 2D materials means a atomic layer, atomic layer. That means the thickness of a layer is in the order of dimension of atom. So maybe there is a single layer or monolayer, maybe there are two different layers. So these are called 2D materials. So instead of oxide, bulk oxide, if we can insert the 2D material based insulator between two metal electrodes, we must have more and more control, and we should reduce the variability. So people have been trying with these materials, say MOS2, MOSE2, selenide 2, MOTE2, etc. And what is the difference, technical difference? The 2D materials, what we are talking about, it is not amorphous nature. That means not is fully stochastic process you have to go through, but it is a crystalline nature. And this is the layer thickness is in the order of atomic dimension. That's why it is sometimes called atom resistor, and this is called atomic layer. And the mechanism is a bit different from the nanoionic film formation. So they are generally in a MOS2, this is a very well-known material. So in MOS2, so there are some sulfur defects. Sulfur defects means the arrangement of molecular arrangement of molybdenum and sulfur. The desired molecular arrangement is missing in some cases, some developed MOS2 films. So these sulfur defects can be controlled or can be engineered by changing the resistance of the MOS2 layer. When you put this MOS2 with the sulfur defects between two metal layers, if you apply some voltage, so one metal atom may migrate from metallic electrode to that sulfur defect. There is a vacancy. So that means if a metal atom migrates from the electrode to that sulfur defects, it will change its resistance. This is the main mechanism of the changing resistance in a 2D material. It will be more, it will be just described in more detail. So now let us see what type of works we have been obtaining in different things, different papers. But where is your scope of work in this particular aspect? So since the resistance from one cycle to another cycle is varying, you can design a circuit that should compensate the random behavior or the fluctuation. There is a one circuit people are doing. Different materials, say number of layers can be explored instead of a single. So material chemistry is very important. So this is one type of interdisciplinary field. I can tell you some device, some material science experts should get together, should sit together and say they should discuss, then only the solution will come out. And but one thing here I should mention. So people are looking always the drawbacks of this randomness, random behavior of this resistance property, but it has a good side also. Actually, we in electronic or electrical engineers always look for some random number generator. So sometimes we don't get any random number generator. That's why we go for pseudo random number generator. But this variation of resistance with a stochastic variation, is a random nature, we can get a true random number generator. Some reports based on true random number generator based on this memristor is also a good area of work. So people have been reported, and this is going on. And also there may be some work may be done on the variation of electrodes, because there is an interface between electrodes and the oxide interface. So interface can be controlled by changing the electrode materials. And finally, to understand the characteristics, the modeling is very important. Modeling means developing accurate model. And that accurate model of changing resistance of the insulator material or 2D material, 2D insulator material due to morphological change is really difficult. It needs the molecular dynamics. It needs molecular level modeling. So that modeling also can be developed as a good as a scope of work. And recently, so Texas AT&T laboratory, so they propose a single defect memristor, which is the lowest size memristor till now based on the MOS2. This is the smallest size number, and they do the experiment simply by putting the AFM tip on the molybdenum sulfide layer. AFM tip means there is a the one gold atom from the tip migrates to the MOS2 and current increases. That means after putting the AFM tip, we are observing the current, it is being increased. So this is the behavior. I have taken their papers. So this is a very interesting. So they prove that. So a migration of metal atom into the sulfur vacancy. So but later on, say a group from the Purdue University, so they totally explained the thing differently. And through the spectroscopy study, they have shown that a 2D material has a different phases. People, you see this layer, here there are different phases, a dark red, then light red, almost yellow-like thing. So different phase means there are different grain boundaries. So this is not fully crystal. 2D materials have some grain boundaries, and in one grain has a different phase than other grain. That is different orientation of atoms, different array of atoms, a particular grain. So due to the different phases, it has a different resistance. And on application of voltage, these phases will change. And that is the result of the changing the resistance in the case of memristor devices. But in a very recent in the Stanford University group, they totally contradict this explanation, and they explain no. So this may be the case of a particular 2D material, but actually they claim that explanation by Purdue is totally this is a fully contradictory thing. Ultimately, what I like to mean that is there is no genuine theory till date. So huge scope of work on modeling, namely molecular model, atomic model for the resistive change behavior is required. And for that, you can take the help of the Schrodinger equation solution for many particle systems. Say, starting from a single particle within a box, if anybody can solve the Schrodinger equation for many particle system, so really it will be good work. And the density function theory, this is a very well-known theory for the chemistry and other things for behavior of the resistive memory, have been evolved, and people have been using this density functional theory widely for this. Now, this is the future prospects. You see, there is a hybrid nature of CMOS memristor thing are there. So because memristors always have some drawbacks, so hybrid technique of CMOS memristor is a good thing, and 3D stacked arrays also is a good prospect, and integration of these memristor with AI edge computing is another area. And I missed one slide. I am just going back. So this is a behavior of the stochastic behavior in the function of density of states. So I can explain here. So actually in MOS2, so there are, so in this as per the molecular theory, if you see the density of states as a function of energy of a MOS2, so there is a gap between a minimum energy to a in the conduction band to the maximum energy in the valence band. So there is a big gap, and this gap actually there is no energy states. But when a metal migrates from electrode to the MOS2, so in this gap some energy states are created. And due to creation of energy states, that means there is a possibility of flow of carrier, that is existence of carrier in these gap states. And that is the basic theory behind this, proposed by this group of people, and also proposed by a renowned scientist, Professor Santanu Mohapatra in IISc Bangalore in India. So that molecular theory, they calculated, they have shown that migration of metal into the 2D material is the origin of changing in memristor or the resistive memory. And so there is a lots of potential, you see, in memory and computing. Crossbar arrays are the key neuromorphic and in memory systems, because crossbar array is required to have a full AI/ML circuit on a chip or neuromorphic computer on a particular chip, self-sustained, no need of computer, CPU, the other memory unit. So itself it will be a single unit having a processor and memory both. And future is promising, but requires overcoming engineering challenges and mainly modeling. Modeling means molecular model, atomistic model. These are very important. So some references I have given, and I will give this as a PDF, as a material. From that you can get, and you can go through the literatures and of these references, and you can get more insight. And because this within this short span of time with a particular technology detailed discussion is a bit difficult, I wanted to give a insight about the different mechanism of memristor devices. So with this, thank you, and I am waiting for some questions from the participants.
Hello. Sir, So thank you, Professor Hukun sir, for delivering such an engaging and informative session. Your slides have added great value of our understanding and spark meaningful reflection on our regarding the topic future perspectives of memristive devices. Now, we would like to invite our participants to share any question or comment or query. Please, anyone want to ask? Sir, from chat happening.
How can I think
Sir, someone is asking about Muhammad Yashin. That how can
no,
memristive-
actually I think sir, could you please explain again the hysteresis behavior of memristor? I got question from some participant. So just a minute. So let me go back to the slide. Here, so can you see? Is it visible?
No, sir, it is not visible. The last
Not
time
visible.
slide is working.
This slide is not visible. Sharing mode is on, continuously on.
Last slide is coming, and this slide is.
Sharing, anybody cannot see the slides?
It is not visible.
Only last
Okay,
slide is.
I am stopping. I've stopped sharing. Again, I am sharing. It is better.
Yes, yes.
Now it's visible.
Okay. So you see, so here we are changing the voltage across the MIM structure. Suppose from this point, so for 0 volt, so 0 current, because insulator in between two metal electrode. Now gradually we are increasing, say 0.1 volt, 0.2 volt, in this way 1 volt, 2 volt. Still very small amount of current is flowing because the insulator between two metal electrodes does not allow you to flow the current. In this way, if we keep on increasing, it is increasing in this way, and at a particular voltage, suppose it is a 2 volt or 3 volt, it may be, it depends on device to device, suddenly we get a very high current. That means at this point of time, that nanoionic film is formed. So there is a path for flowing the current from top electrode to bottom electrode. So we are getting very high current. That means the resistance becomes very low. If you take, this is along y-axis, there is a current, along y-axis, there is a volt. So if you take the slope, so inverse of slope will be very high. Del I by del V, and you know del I by del V is the R inverse. So it reaches, suppose, at the tip of the arrow here. Now, without further increasing, we are reducing the voltage gradually. Say from 3 volts, so gradually 2.9 volt, 2.8 volt, 2.7 volt, in this way. In that case, if we observe the current does not change. That is the film whichever has already been formed, that is not being broken out. That remains intact. So now, if you reduce the voltage from 3 to 2.8, 2.76, in this way, it remains intact until a particular value is reached. Suppose in this voltage, say 1 volt. Now, these gradually the formation of films, whatever the film formed, they are gradually vanishing. So one by one, they are the vacancy, like oxygen vacancy, are being distributed throughout the device. So its in resistance increases. That means current decreases. And this current decreases in this following this path linearly almost, and it comes down to zero at again 0 volt. If it is not 0 volt, some initial things are there, then at 0 volt retracing you may not get the zero current. Some inertia, due to some inertiative action, some film formation may be there. So in that case, you can get a small amount of non-zero current. It depends on again the things. So ultimately, if you see the tracing time and retracing time are not same. Tracing path and retracing path are not same. So that indicates there is a hysteresis. So some permanent change is there. This is called permanent change, and that is happened in origin of hysteresis in magnetic field also. If you keep on increasing the magnetic field, any magnetizing material becomes magnetized, and if you remove gradually the magnetizing force, it magnetic property will not remove completely, it remains something. So that is called the hysteresis thing. So loop hysteresis area under this loop, and also at the 0 point you can get a non-zero current. Earlier it was zero current. So to get the zero current, you have to apply some negative voltage again. That is you have to apply a voltage in a reverse direction to completely break down the nanoionic film. So this similar happening in the reverse side also. So this is the origin of hysteresis. How can I get the code for memristor to implement logic gate and crossbars? So these are available in many things, websites people are working. You can do, but I would suggest you to develop your own program. Otherwise, it will not be meaningful and is a contributory. Yeah, you are like to means the source or software source. This some cadence virtuoso is there. Yes, I mean in cadence virtuoso. Yeah, some softwares are there. So quantum espresso is there. Quantum espresso you can do some modeling and some development there. So, sir, you said that atomic layer thickness will reduce the cycle to cycle radius. But, sir, could you mention that what will be the range of thickness in nanometer of the insulating layer in MIM structure? Yeah, in nanometer, if you, in an oxide case, if you reduce below the 20 nanometer, in that case, there is a chance of leaking. Leaking means insulation leaking things. So that you have to take care of. But in MOS2 layer, you can reduce it up to the atomistic, that is 2 to 4, 5 nanometer, you can reduce, no issue. But in oxide case, below 20 nanometer, it's a difficult problem due to amorphous nature and this leaky nature. Sir, both RAM and capacitor have MIM structure. How do they function? Thank you very much. So while designing memristor-based hybrid logic circuits with CMOS, whether the memristor works as linear resistive switch, particularly in digital logic. In case of digital logic, memristor offers non-linear thing, sudden change is there. But in analog computing, memristor will give you the linear change in resistance value. Linear resistive switch, no, linear resistive switch is and for analog computation. Is there an optimal concentration of oxygen vacancies for achieving both low power consumption and high endurance? So this oxygen vacancy, no. So there is a maximum value, but to obtain this maximum value, we have to go through the experimental study to get the oxygen vacancy. But this value will differ for different materials. So for TiA2, for gallium oxide, it will be different. For graphene oxide, it will be also different. I'm not sure whether memristive circuit models are available or not. I am basically from device perspective, and a device model, I know DFT calculations are being done, not at the circuit level. I am really sorry, but in device level, you can get some quantum expression like things for modeling it. DFT, I have avoided the DFT, including the huge mathematics and a very boring mathematics also, the Schrodinger equation. If anybody interested, please you may drop a mail to me. I can help you, or I can have another meeting to guide you or to show how the calculation is there, because this is very very boring and is time taking. Is not a generic lecture in that case, it would not. Without chat, anybody can want to speak something regarding the question and the things. Professor Rajiv, are you here?
No, sir. But somebody, if you anybody ask some question, they may ask to sir directly.
Somebody means in chat I have gone through.
Okay.
But any direct question from the audience?
Sir, all through the lecture, it was very informative. We have learned so many things, and definitely we will be get benefited in future. It was very informative session. And, according to the queries and questions, these are the general queries from us also. So it was nice. Thank you, sir.
So 1 minute, just a minute. So okay. So can I leave this call or this thing?
Yes, yes, sir.
1 minute.
Thank you very
Okay,
much, sir.
so I think it's okay. So from here I have to leave, no? So I am putting my mail ID. So you, because in this short time, if anybody interested, I can discuss you in future through email and through another meeting, etc.
You can write in the chat box.
Okay. I'm leaving now, Tab. Then.
Yes, sir. Thank you, sir. Have a nice day. Now we are binding today's sessions. From tomorrow onward, we will be sharply start our lectures from 9 a.m. onward. So tomorrow at the beginning, Sunmo Kang sir will take the lecture, and followed by Sir Rajiv Ranjan will take the other lectures and tutorials. Okay. So today's session we are stopping here. Thank you for joining. Hello, sir.